All right, third attempt to record this today. There's always been a child or something on the way. I think I'm being a bit a victim of impatience, right? Because I've invested so much time on the videos already that I'm like, I gotta be close to at least solving that one problem. And I have the feeling that's where that's where you know that's where that's where I'm getting stuck, right? Because I the thing is where did I leave that? So that part here where I spend so much time is actually it's actually just the easy part. Maybe I just wasted too much time. Maybe I just wasted too much time trying to compute things and whatnot. But I'm learning how to use AI here the best possible way. And I think calculating the blocks is what's going to be complicated. Look at these. So because I couldn't do the video earlier today, what I did is I actually started talking to Grok about it. So I I started this thread, and essentially got to a point where we talk about conjugacy classes. Then we talk about these. So that's interesting, right? So because at the end, it's like I had the feeling Grok is telling me that I should be computing first the representations of G over the complex numbers. A few things I want to ask Grok. Okay, a few things I want to ask Grok. And we're gonna use Grok 4 fast. We can try one thing actually. Can it just one-shot it? One-shot it. That's one thing. We'll keep it running here. See what it does. Because Grok 4 fast is supposed to be like a hybrid of like reasoning and not reasoning. And let's see. Maybe just one shot's the problem. So that's good. So let this run here on the side. And what I want to do is I want to do the following. I want to I'm distracted today. I want to do these. I have this group G. So Y over C. We compute ordinary E-reps over C. Char 0 algebraically closed. Okay. So let me start here by doing these. So here we've got the definition of G, right? Somewhere here we've got the definition of G. So and now no, look, it actually didn't, but 39 seconds. It took Grok 4 like 15 minutes to get to the same conclusion. Explanation. Sagro. Does not derive at 27. I think that's the mistake. Because we're looking at a group G which has 108. And so my theory, I mean, this is definitely, okay, so it got 11, which is the wrong answer, okay? The right answer is 5. The right answer is 5, right? 5. Then we are at the point where if I look at this conversation and I forgot where it is, it basically says so these are different strategies, right? So if for finite groups, use these. And then there's something else if f is not dividing the size g. But in this case it is, right? Because we have char is 2 and then g is 1 and 8. Use character tables. But anyway, so let's think of strategies. Maybe I don't want to. Do I want to pollute? Do I want to pollute the context here? I don't want to pollute the context here. So what I want to do, new chat, create share link. I'd love I could just clone these. Start thread. Oh, okay. Okay, that's new, is it? Okay. Start thread. All right. So that starts a thread. I want to develop a strategy to calculate or to calculate the IREPs of G over a field of chart 2. Where should I start? I've heard one way to do this in our case, because 2 divides 108, is to first find the reps over the complex, because char is 0 and closed algebraically, and then we can work our way up to a chart 2 field, because then we're getting to this modular. So this is essentially what Grok was telling me, that then you're getting to modular modular representation theory. To be honest, I'm lost. This is like if I all of a sudden just opened up a huge can of worms. I don't have frames of reference. That's why I'm losing so much time, because I'm like, to find representations of a group G over field F, for finite groups, do these. For explicit construction, map group elements to matrices, find group relations. And induced representation, start from a subgroup rep and induce to G. Okay. For a billion groups, not interesting. For using Maschke's theorem, not interesting as well either, because of these. And then check books. Where did I start the thread? Here? Yeah. Can you give me a few strategies to approach this? All right, so we actually have threads. That's good. I never noticed that, so it's either new or I don't know. Okay, but grok 4 fast, I can't decide not for it not to search, but maybe that's the best way to do it, right? So your group this makes the modular representation theory more involved than the ordinary case, characteristic 0. And we deal with Brouwer characters, whatever that is. Okay. Ordinary characters. I don't know what characters are. You're correct. The one standard approach leverages the ordinary representations over C or algebraically closed fields of char 0 as the starting point, then reduces to char 2 using Brouwer theory. This works well because the ordinary theory is well developed for small groups like yours, and the reduction provides information about the modular IREBs, autoprojectives, and blocks. Below, I'll outline 4 practical strategies to compute the IREBs over char 2 fields. So we've got Brouwer reduction from ordinary representations. We've got smaller group. Then we've got strategy 2, Clifford theory for normal subgroups. Exploit the semi-direct structure directly in modular case. Use the normal subgroup D to build modular reps with Clifford correspondence. Block theory and defect groups focus on 2 blocks. Decompose F2G into indecomposable blocks, then find the simple modules within each block. Computational verification with induction. Start with strategy 1. It's the most straightforward and aligns with your idea. So it's not my idea really, but compute the ordinary table using the semi-direct structure. Expect 4 1 dimensions, 3 2, 2 3, 1 6 IREBs or similar. Then apply Brouwer reduction if you have access to gap magma. That's ideal for verification. Otherwise, manual induction for the semi-direct product. I do have gap. But I want to learn 2 things first. First things first. Brouwer reduction. First, I want to understand what the characters table is. I need to understand that, what the characters table is. Can we characters table? For these, I'll use a new thread. No. What's the group theory? Character tables in the context of a group group. Here. It's a tabular summary that captures essential information about the irreducible representations of a finite group G. So how are they constructed? Identify the conjugacy classes, find the irreducible representations, compute the character values. conjugacy classes. Number of conjugacy classes equals to number of reducible representations. Find theory representation theory. This can be done via methods like induction from subgroups, explicit construction, permutation representation, and computational tools. For small groups, is often feasible by hand. Can you show me? Can you give me gap code to compute the chart table of S3? Because I do, as I said, I do have gap, right? Copy. Okay. So it's not exactly that, but it has output it is. So defines a symmetric group S3 and computes this character table using the built-in character function running. Okay. But let's understand that better. So a character table is a tabular summary that captures essential information about the irreducible representations of a finite group. Representations are homomorphisms, GLV, from the group to the general linear group over a vector space V. Typically, same for complex representations. The character of a representation, okay, so that's what the character is the function. Okay, so the character is the function that translates an element of G to the trace. Okay, the trace of the matrix representing G. Why? Why is that? So, so character tables focus on irreducible characters, which correspond to irreducible representations, those that cannot be composed into simple representations. Yeah, it's still, but you still have to construct the table, which already means finding. So, identify the conjugacy classes of G. Find this is something that it just seems like it's easy to compute. Then find the irreducible methods like induction from subgroups, computational tools. This looks like you should be able to do with gap then, because identify the conjugacy classes. And then this is just like an algorithm that gives you the conjugacy classes that fulfill these. These are the sets that fulfill these. I don't know intuitively why would the why does the number of conjugacy classes equal the number of representations? Let's dive into this. So the conjugacy, can you drill down and focus on the concept of conjugacy class its definition. So in theory, conjugacy is a fundamental equivalence relation that groups similar elements together based on how the group itself can relabel or transform them. This concept is crucial in representative theory because it simplifies computations. Many properties, like characters, are constant across these classes. For group G, two elements G and H are conjugate if there exists some K. Okay, so they are conjugates if... That's interesting, because like, why? This feels really random, actually. This feels very random. So in terms of why would you define a concept like this? So two elements G and H are conjugate if there exists some K also belonging to G, such that doing the inverse of K time and then G and then applying K would equal H. I guess in a way this kind of feels like it's for some reason in my head I have like there's a way to go from G to K to H, from G to H, right? Because essentially what it means is if we are applying K inverse and then G and then K again, because you know, think of these things as like, again, these things are transformations, right? These elements, the elements of a group, are kind of transformations, right? So if you apply an inverse, and then you undo it with K, then you get H. It means they're conjugate. So the conjugacy class of G is denoted CLG, or sometimes just G, is the set of all elements conjugate to G. So all elements okay, so you take G. Okay, so you take G, you apply these transformations. Okay, yes. Now I see why this makes sense, because actually you're really building transfer, like you're looking at, yes, that makes sense. Okay. Essentially you're looking at all the reachable areas of your group from that element, right? So and again, I'm a bit spoiled because the way that I'm interpreting this intuitively, it's kind of a little bit a build up from my videos in the past years studying quantum computing, where you have the transformations and then often you just, I don't know, maybe it's the wrong way to look at it, but somehow it's like that's what what a group is, right? So that's what a group is. I mean, a group is just a set of elements. These elements represent transformations. And actually, when you're doing this representation theory thing, is exactly what you're doing. You're instantiating these representations, right? The only thing the group is telling you is it's giving you structure over these transformations. Right? I think so. So essentially you're defining, you're like looking at G and you're defining basically you're defining all the elements that you can get to by by applying I mean the choice of k to the minus 1 and k still feels a bit random. The example in S3, symmetric group of on 3 letters, permutations of 1 to 3. The identity is one class. Then we have 2 cycles, 1, 2, 1, 3, 2, 3. These are all conjugate. These are all conjugate because what? Because conjugate 1, 2 by 1, 3. One, two, three, 1, 3, 2, conjugate 1 to the other via 1, 2. Two cycles, 1, 2, 1, 3, 2, 3. They capture a notion of structural similarity. Imagine the group elements as symmetries of some object. Conjugate elements are those that look the same after relabeling the object's labels to another symmetry. Okay. Yeah, that is also an interesting way to see this. And then that's the intuition view. The algebraic view is an inner automorphism. Classes are orbits under the action of G. The equality of dimensions. Okay, the Birdseye theorem. Okay, let's not go too far. Let's linger in these for a little more. What does it mean to conjugate in math? In the context of complex numbers, the conjugate of a complex number a plus bi is a minus bi. So it's like a mirror, right? Yeah. Okay. Measures similarity under group action. Conjugates form conjugacy classes. A conjugate is the inverse of, in this case, the inverse, then the thing that we're trying to conjugate, and then the normal thing here. So you're conjugating by a number. Aren't you just mirroring in a way, like in the group theory view? Are you sort of mirroring against a concrete G? Yes, yeah, exactly. Kind of mirroring, like a reflection. Okay. So so essentially conjugation in this sense is, yeah, it's basically I have a group, and if I want to calculate all the conjugacy classes, I'm looking for the groups that basically everything where everything is just sort of a mirror of itself. And actually that makes sense because, and this is also in par of with like this view here of like what was the view here, whatever, you know, the view that it's basically is the view that it's basically the mirror. Yeah, it's the view that it's basically um like relabeling a relabeling a uh like a symmetry. Yeah. um so I'm gonna wrap it up here now. I just because I don't have more time, sadly, but step by step. All right. So what we have is the following. We have. That's all right. Okay. So let's do this. It seems, I don't know exactly why, but like I think doing these conjugacy classes makes a lot of sense, because these things will then be respected by the representations. This means, in a way, obviously, these things kind of form groups that when you then do the representation, they probably generate the groups, right? So the blocks, I mean, it kind of like, in a way, this must be related to the blocks. Exactly. In a char zero field, right? In a field that intuitively somehow makes sense, right? So you find the conjugacy classes, and that, like, if your field didn't have a characteristic, remember the characteristic is this thing that then there's like an element where it's like 1 + 1 = 0 or something like this. So a kind of modularity. If your field doesn't have any modularity to it, then you're done. Then these are your irrep classes, and then these are your blocks, really. Now, what we're going to try to do, I'm thinking what I'm going to try to do is basically the strategy should be do these and then try to work our way to chart 2. So let's close this thread. It's nice because you can actually access the thread here. This is actually nice. This is very nice. Can you give me the gap code to construct G as we have defined it in this conversation? Let's get to these first. And then we want to compute the conjugacy classes. I think that's something that gap should be able to do, because that's just very mechanical, right? It's just taking every element and then building those classes. So I'm hoping that I can do this and I can just close for today. And then we have the conjugacy classes. And then we need to find a way to reduce from that to like char 2. That actually, I've just put a lot of pieces in place, because now I understand that you can find the shadow of these blocks. You can find these structures inside the group with these conjugacy classes. Everything that kind of is a mirror of itself will then end up into like creating a block, because all these operations are mirrors of themselves, and that will naturally create a block. Yeah. So a Boolean group, generative group, I don't know if that's true. Construct a client for a group, define the automorphism. Okay. Let's try this. If it doesn't work, I'm going to stop here anyway, okay? So, Can I start a new session? I should start a thread. That's good, I got these. I wonder how threads are considered for the overall context of the conversation. I guess what I like is that it does not pollute the main thread. All right. Should pin this one. At least I'm happy because that has really been copy gap file, new session. Okay, it's fine. We'll continue in the next session. I don't have more time. See you. Bye-bye.